Hey, take a quick look around you. The device you're watching this on, that bottle of water, maybe even the chair you're sitting in, chances are plastics is all over the place. But here's the thing, not all plastics are created equal. So today, we're going to dive into the fundamental differences between these materials that, quite literally, shape our world.
Have you ever really thought about this? I mean, a plastic water bottle will get all soft and gooey if you heat it up, but the handle on a cooking pan, it won't melt. It'll just char and burn. They're both plastic, right? So why do they act in completely opposite ways? That is the big mystery we are going to unravel today.
All right, so to get to the bottom of this, let's meet the first of our two main players. This category is called thermoplastics, and as you might guess from the name, they have a very special relationship with heat.
The key is right there in the name, thermo for heat. So at room temp, they're solid, no surprise there. But when you turn up the heat, they get soft, they start to flow. This is what lets manufacturers inject them into a mold to create pretty much any shape you can possibly imagine.
But here is the absolute magic trick, reversibility. This isn't a one-time thing. You can take a thermoplastic product, melt it all the way down, and then reshape it into something new. And you can do that over and over again. This property, this ability to be reformed, is the very heart of plastic recycling.
And trust me, these things are everywhere. You've got polyethylene, PE, that's in your shopping bags and milk jugs. Polycarbonate, that's what makes eyeglasses and CDs so tough. And of course, PVC, which is in all those pipes and window frames. All of them can be melted down and remolded. Okay, so if those are the plastics that can be remolded, what about our panhandle? Well, that brings us to our second category, thermosets. You could say that if thermoplastics are all about change, thermosets are all about permanence.
Now with thermosets, the initial process also uses heat and pressure, but what happens is totally different. It's not just a physical change, like ice melting into water. It triggers an irreversible chemical reaction. The material gets cured or set. It's like baking a cake. And once that cake is baked, there's no way you're turning it back into batter. It is a one-way street.
So where do you find these guys? Well, anywhere you need serious durability and heat resistance. You'll find bakelite in electrical insulators for one simple reason. You absolutely do not want them to melt. That tough surface on your kitchen countertop? Probably melamine. And the super strong epoxy resins used in high-performance gear? Classic thermosets.
So one type melts, the other just burns. What is going on here? Why the huge difference? Well, the secret isn't something you can see with the naked eye. It all comes down to their molecular structure.
And honestly, the best way to picture this is with a pretty great analogy. Think of thermoplastics as a big bowl of cooked spaghetti. The long polymer chains are all tangled up, sure, but they can still slide past each other, especially when you heat them up. That's what lets the material flow. Now think of thermosets as a net. During that curing process, strong chemical bonds form between the chains, locking them together into this rigid, cross-length structure. They're locked in place. You can't make them flow. You can only destroy the net by burning it.
Okay, so let's put this all side by side. That spaghetti structure of thermoplastics makes them flexible and impact resistant, but the rigid net of thermosets makes them strong but brittle. And here is the absolute key difference. Thermoplastics will melt before they break down, which is why we can recycle them. Thermosets with that locked-in structure will just burn. They degrade before they ever get a chance to melt, and that is the answer to our panhandle mystery.
But wait, it's not just these two. The polymer universe is actually way bigger. There are some fascinating specialists out there that kind of blur the lines and open up a whole new world of possibilities.
First up, let's talk about elastomers. You can think of them as living somewhere in the middle. They have some cross-links, kind of like a thermoset, but the links are really loose and far apart. And this gives them that unique, rubbery quality we know as flexibility and elasticity. This quote just nails it. It really captures their superpower perfectly. They can be stretched out easily, but they snap right back to their original shape when you let go. That's the essence of elasticity, and it's what makes materials like rubber and neoprene so incredibly useful.
Okay, but what if you could take different materials and combine them to create something superhuman? Well, that's when you get the power couple of the materials world, composites.
You see, a composite is really a team effort. You've got the polymer matrix, usually a thermoset resin like epoxy, that acts like the glue, holding everything together and protecting it. And then, embedded inside that matrix, you have reinforcing fibers, like carbon or glass.
and their job is to provide just incredible strength and stiffness.
Just how strong are we talking? I mean, look at this chart. It's just wild. Your standard steel has a tensile strength somewhere between 400 and 700 megapascals. But a carbon fiber composite? It can be over 3 times stronger, easily topping 2,000 megapascals, and it does all that while being way, way lighter. This is exactly why it's the go-to material for aerospace and Formula One racing.
So, we've gone from a simple water bottle to a tough-as-nails panhandle, all the way to advanced racing components. What's the big takeaway from all this?
It all comes down to this. Understanding these differences isn't just academic. It's absolutely fundamental to how we build our world. Do you need something to be flexible or rigid, recyclable or superheat resistant? Knowing the difference between a thermoplastic, a thermoset, or a composite is what lets us design and engineer everything around us. So the power is in your hands now. You can basically see the world through the eyes of a material scientist. The next time you pick up any object, ask yourself, was this designed to be reshaped, or was it forged in fire to be permanent? Is it spaghetti, or is it a net? The answer is right there, hidden in its molecular chains.